Welcome to today's lecture. We are going to prove Tate's theorem, but before we do that, I'm going to recall some preliminary results on division algebras. Okay, so this is I call this section semi-simple modules, and so in this setup, so all the ring in this section have a unit element. And then if F is a ring homomorphism, then that means that F will send 1 to 1. Okay. So, and then so we in this most ring here will be non-commutative. So most ring will be non-commutative. And so if A is a ring, so we let A be the opposite ring. And then ZA will be the center of A. Okay. So the first definition that I want to say is the following. So from now on, A is a ring. And then I'm going to say that, and then I'm going to let M be a non-zero left or right module on A. Right, so then I'm going to say that M is irreducible or simple So M is irreducible or simple if the only non-zero left respectively right submodule of M over A are 0 or M itself. Okay. Okay. And then we are going to say that M is semi-simple if every left so if every left respectively right is submodule of M is a direct summand. Okay. So the first lemma is give us the first properties of semi-simple module. So lemma, first lemma, I'm going to call it lemma 1. So we let A be a ring. And M a non-zero I'm going to say left module, but it really doesn't matter. Right, A module. Then the lemma says the following. Then M is semi-simple. Semi-simple if and only if there exists a finite set I'm going to call finite set Mi, I in I, of simple module, of simple A modules, such that M is the direct sum of those simple modules. So this is something which follows easily from the definition. So I'm going to leave this as an exercise. And the next definition that we are going to give is that of a simple ring and a semi-simple ring. So we say that A is a simple ring if the only two-sided ideal ideals of A are 0 and A, oops. So if the only non-zero two-sided ideal and A itself, oops, Sorry about that. And B, so we say that A is semi-simple if every left, and I guess you say right, A module is is semi-simple. Okay. Okay. So now a quick lemma. So this is the second lemma. So let A be a non-zero. Then A is semi-simple if and only if A is semi-simple as a left right A module. Again, so far most of these result follows from the definition. So the proof would be left as interesting exercise for you to go over. And the first thing that I want to say is that so if A is semi-simple, then we see that so you see that there exists finitely many many here, and the key thing is that minimal non-zero ideal. So minimal non-zero ideal, which I'm going to call A1, A2, up to AR. And each of all contain in A. And the key thing is that each of these ideal is also a ring, and which this ring is simple. Right? And so as a result, we see that A will be isomorphic to the product of these ring. So in other words, every semi-simple ring is a product of finitely many simple ring and vice versa. And the converse is also true. Conversely, a finite product of simple ring is a semi-simple ring. Okay. So that's the first properties of semi-simple ring that we're going to see. And now, as a consequence of this, we have the following proposition. So if you let A be a semi-simple ring, then up to isomorphism, there are finitely many simple A modules. There are finitely many simple A modules. Again, this is the proof is essentially an application of all the definition that we've seen so far. And I'm going to leave this as an exercise for you. Okay. Now, so again, so let A be a simple ring. And we are going to let M be a simple module over A. Right? And then I'm going to let D be the endomorphism ring of M. Right? Then, because M is simple, you see D would be a division algebra, then a division ring. Right. Okay. And this division algebra has a name, so we call D the commutant, of A. And we call the endomorphism ring of M over D the bicommutant. So we are going to say that these two rings help us describe the structure of a simple ring. And in order to do that, we are going to proceed as follows. So see, if I take, let's say I take an element of my ring A, And then there is a way to associate an endomorphism to that element. And so I take an element, and then I'm going to let A sub M be the endomorphism of M over D, which is given as follows. So what this map does, so it's a map that goes from M to M. And then, so this is A, M. And then when I take X here, I map it to AX. So this is clearly a map. So this is clearly a homomorphism, and this homomorphism belongs to the bicommutant. And the lemma here says that this is basically tell you how to describe any this map that we just defined give an isomorphism which basically describe our simple ring, right? So this is our third lemma. So if I let A be a simple ring, and M a simple A module, and I'm going to let D be the commutant of so then the lemma says that this map that we just saw, so the map that goes from A to the bicommutant, sending A to AM. So this map is an isomorphism. So is an isomorphism of A onto its bicommutant. So basically, if I want to describe, if I have a module, a ring A, and I want to describe that module, if I can find a simple A module, then I can describe A by computing it bicommutant in terms of that simple module. And as a result, we have this corollary, which is often known as the Wedderburn theorem. So this corollary is Wedderburn. So let A be a simple ring. If A is a simple ring, then there exists an integer which is at least 1, and a division ring D such that A is isomorphic to Mn to the D, so MND, where MND is the ring of sorry, the ring of n by n with coefficient in D, right? So let's prove this, right? So let M be a simple module over A, right? Then you see A would be, A has finite length, has an A module. And what that means is that, so there is an integer n such that A would be isomorphic to n copies of M as an A module, right? And so what we have to do, we just apply the lemma we prove. So from the above lemma, we see that A will be isomorphic to MND. Okay. And the key thing is that the converse of this statement is of course true. So so this should be an if and only if. So if I have a matrix algebra with coefficient in the division ring is a simple module. Okay. Yeah. So I'm going to restate the lemma we saw as a theorem. We stated the lemma for a simple ring, but I'm going to state it as a theorem. I think this is the second theorem. This is known as the bicommutant because we're going to need it. The bicommutant theorem. So we left A be a semi-simple so A is a semi-simple ring, and M an A module of finite type. And then we let C be to the endomorphism of M over A. So that's the commutant. And we view so we view M as a left C module by setting C time M is equal to Cm for all C that is in C and M in M. So then the theorem says that this map is then the map that goes from A to the bicommutant, sending A to A sub M is an isomorphism. So as I said, we prove this lemma in the case when the ring is simple. So the proof really isn't different in this case. Okay. So to finish this section on semi-simple ring, we're going to state the Skolem-Noether theorem, which is a very important result in this area. So it says the following. So let A be a simple, let A be a simple algebra over a field over K, its center. Oops. Over its center K. So with center K, and then we let B prime be simple K algebras. Oh, sorry, K subalgebra, sorry, I mean. Of A, and of course of finite dimension over K. Then, so the conclusion is that for every isomorphism, of B to B prime, so if this is an isomorphism of K algebra, there is there would be an inner automorphism of A. So we're going to call that psi of A, such that if we restrict phi to B, sorry, phi is the restriction of phi is the restriction of psi to B. Okay. So this is a theorem that we're going to need later. And so for now, this is what I'm going to say about division algebras. And I'm going to supplement this basic fact as we go along. So every time we need new stuff on division algebra, I will supplement the stuff we need. And then by the end, we will see all the stuff we need about division algebra for the proof of the under-Tate theorem. Okay, so let's go back to Tate theorem, which is the topic for today. So Tate isogeny theorem. So this is, I guess I should call this 3. Okay. So the first thing that I want to recall is if you remember last time, we saw that the endomorphism ring of a simple Abelian variety is a division algebra, and that and so we are going to need that today. So the first proposition that I'm going to state is the following. So let A be an Abelian variety over K. And then I'm going to consider the degree map. So remember, we defined the degree map on isogenies. So it's a map that is valued in Q. So if you take an element in this endomorphism ring, then it goes to C times the degree of phi. So in this case, C is in Q, and then phi is an isogeny. Okay. And so the proposition says that this map is given by a homogeneous polynomial function of degree 2g. So the degree map is given by a homogeneous polynomial function of degree 2g, where g is the dimension of our Abelian variety. Okay. So by homogeneous, I mean that if I take the degree of n times phi, this would be n to the 2g times the degree of phi for all n in Q and phi in okay. So we are not going to prove this proposition. The proof is actually a bit involved, but I can give a reference if needed. So using this, we can define what we call the characteristic polynomial of an Abelian, an endomorphism. So let A be an Abelian variety over K. then for any endomorphism, so for any element in the endomorphism ring of A, there is a polynomial which we call p phi of x, and this polynomial is a polynomial with rational coefficient. It has degree 2g, such that when I evaluate this polynomial at n for any rational number, and then what I get is the degree of phi minus and this for in Q. I think maybe I want to say Z, even if I think that this should be okay. Okay. So now this is, we call this polynomial the characteristic polynomial. So we see that if phi is an element of, remember the difference between n superscript 0a is that this is the tensor product of the endomorphism by Q. So if I take an element in the endomorphism ring, then the polynomial, this polynomial would be a monic polynomial. So it's monic, and it will have integer coefficients. Okay. And so we call this we call this polynomial the characteristic polynomial of the endomorphism phi. Okay. And use we can write this polynomial, so we can expand this polynomial. So we can expand. So if I take P of phi applied to x, it would be x to the 2g. And then here I'm going to, the first element is what we call the trace. And the last element will be nothing other than the degree of phi. So this is the trace of phi. Okay. So there are several ways of defining the characteristic polynomial of an endomorphism. I mean, one indirect way is by using Tet module, but we are going, the next proposition is going to say that this polynomial is actually related to the Tet module. So the next proposition, I think my numbering is completely wrong now, but anyway, so So let A be an abelian variety over a field K, and then phi an element of the endomorphism ring. Then this says that for if I take a prime which is not equal to the characteristic of my base field, then if the characteristic polynomial of phi is also the characteristic polynomials of phi acting on is the characteristic polynomial of phi acting on the Tate module. Why do I keep? Not sure why I keep. Okay. So it means that the trace and the determinant of this phi acting on VL that can be described directly in terms of this polynomial that we obtain in a different way. So this is not something obvious a priori, but it's one of those striking properties of endomorphism ring of abelian varieties. Okay. So from now on, we are going to let our field K would always mean the finite field with Q element. So it's a finite field with Q element. Here Q is equal to P to the N, P prime, and N an integer. Okay. And then we are going to let the algebraic closure, we're going to denote this by F simply. Okay. So now, so if we let V be an algebraic variety, so over our field K, then we can define so the Frobenius map, which we're going to denote by pi V from V to V, is defined so it's defined as the identity on the underlying topological space. So topology, underlying topological space, and the map we send F to the Q on the structure shift Okay. So a more direct way, so there is actually a more direct way to define this map. So assume that we have, assume that V is just the projective space. So if V is the projective space, P, let's say PM of our finite, simply PM, sorry. So we can write this as proj. When I write too fast, I tend to scramble my writing. So let's say V is this, then we can, then pi V is given by, so by the map on point. So going from V, which is F, and if I have a point x0, xm, I send it to x0 to the q, xm to the q. Okay, so that's so it's actually, so the map can be defined concretely very very easily. So if so in particular, so when V is projective, meaning that it's contained in this PM, then pi V is induced by is induced by the map above. Is induced by pi of PM. Okay. And we see that if I'm looking at the point, this would simply be the set of fixed points. For pi V going from V F to VF. Okay. Now, this map turned out to be a very important map when studying abelian varieties over a finite field for the following reason. So let A be an abelian variety over FQ. Then we see that, so we see that pi A of 0 is equal to 0. Right. And so as a consequence, pi A is an isogeny. Right? Pi A belong to and we are going to let FA be the characteristic polynomial. So we let the characteristic polynomial of pi a. Okay. So of course, from what we just said, this is a polynomial of degree 2g, where g is the dimension of our Abelian variety. It has integer coefficient, and it has integer coefficient. Sorry. Okay. And by the corollary that we just saw earlier, this would be the characteristic polynomial of the Frobenius acting on the Tate module. Okay. So this is the characteristic polynomial of pi a acting on VL of a for L different than P by the lemma. So we call this the characteristic polynomial of geometric Frobenius. So the characteristic polynomial of geometric Frobenius. Okay. So now the first result that we are going to state is the following proposition. So A is an Abelian variety over Fp, oh no, sorry, Fq. Then the first statement is that if L is different from P is prime, then the Tate module, sorry, the Tate endomorphism acting on the Tate module is semi-simple. So this is a semi-simple automorphism of the Tate module of A. So that's the first part of the statement. And the second part of the statement is that if A is elementary, so A is isogenous to where B is simple, so sorry, the notation is isogenous over FQ, where B is simple, then if you take the ring obtained by adjoining pi to Q inside the endomorphism algebra of A, then this is a field. And the characteristic polynomial is a power of the minimal polynomial so the minimal polynomial, I'm going to call it G of pi A over Q. So again, this is really something that you would expect, right? So you have a diagonalizable matrix acting on a space. Then you know that the characteristic polynomial of that diagonalizable matrix would be a power of the minimal polynomial. So that's essentially that statement in the context of Frobenius of an Abelian variety. So the proof again here is really not that difficult, so I'm going to leave it as an exercise. And there are I mean, the proof is in the notes anyway, so you can have a look if you can't do it yourself. So now, the first important theorem that we're going to need, and so let K be a finite field. Right? And G an integer, then, sorry, not G an integer. So, yeah, sorry, I should say. So this is one of the key theorem that we are going to need in the proof when we prove the Tate isogeny theorem, which says that up to isomorphism, there are only finitely many abelian variety of given dimension over any field. So in this case, we only deal with finite fields. So let K be a finite field. Then for any integer G, there are only finitely many isomorphism classes of abelian varieties of dimension G over K. So we are not going to prove this theorem, not that it's extremely hard, but it's just a bit long and require quite a few things. But it will play a key role in the result that we are going to need in the proof of the Tate theorem. The first lemma that we are going to need in addition to this theorem is the following. So again, so K is a field with separable closure Ks, and L a prime, which is different from the characteristic of the base field. Right. So the first part of the lemma says that if A, B are abelian varieties, then the map which we saw last time, and we call it TL, which goes from not sure why I keep the map from ZL tensor with OM0AB So this map is an isomorphism if and only if the map we obtain by tensoring with QL is an isomorphism if. So the map is an isomorphism. So that's the first part. And the second part says that assume that for every abelian variety, so assume that for every abelian variety, C over K, the map if I tensor QL with the endomorphism ring of C to the endomorphism of gal over gal KS K of VLC is an isomorphism then the theorem says that then the mapping not then the mapping so okay so this is star then the mapping star is an isomorphism for any two abelian variety AB. So basically this is a reduction lemma. So we want to reduce the proof of the third theorem to proving this for endomorphism rings. So that's essentially the content of this lemma. And the proof is fairly the proof is actually fairly easy. So the first part follows from a theorem that we saw. We saw that we already saw that the map TL is injective. And we also know that so we also know that QL is flat over ZL. So if combining these two, so this gives the first part. Okay. Now the second part. So the idea is to again reduce the proof to working with the endomorphism ring, and what we do. So take C to be the product of A and B, right? Then if you look at the endomorphism ring of the endomorphism algebra of C, so using what we discussed earlier, then you can write that as a direct sum. So okay, so we got this decomposition, and you can do the same for Tet module. So if I, just to make notation easier, I'm going to let gamma be gal ks over k. We have a similar decomposition for Tet module. So we have a similar decomposition for Tet module, and this decomposition is saying that if I look at the endomorphism of my Tet module, VL over C, it's going to be the endomorphism ring over gamma VL of A, direct sum with home gamma of VL of A, VL of B, direct sum of home gamma VL of B, VL of A, and then finally the endomorphism over gamma of VL of B. Okay. And the Tet map is compatible so the Tet map, which in this case goes from QL to the endomorphism ring over gal ks over k of VL of C. This map is compatible with the decomposition. Right. And so combining this, from this we get the result. So from this, it follows that if, so let me call this, it follows that if VL, so I'm going to call VLC, if VLC is an isomorphism, so is the map QL tensor with home of QL tensor with home AB into home gal ks over k VLA VLB. Okay, so that's the proof. So it's really just some kind of a lengthy calculation, but nothing really difficult. So it reduces the proof of Tet theorem to just work with endomorphism rings, and that's what we're going to do. And before we do that, we are going to state one lemma, which is also not that hard to prove, but the proof is just a bit long. So so let A be an Abelian variety over K, and L is a prime which is different from the characteristic of the base field. And then, so the lemma says that if W is a QL subspace, which is also a Galois module, so if it's stable under the action of gal K S over K, then there exists U in QL tensor with the endomorphism ring of A, such that W is just the translation of VL by U. Okay, so let's prove. I'm not going to give the proof of this lemma, but it's yeah, as I said, it's a long proof. It's really not hard, but it's just keeping track of all the things. So I'm going to give a reference if you want to have a look at the proof. And we are going to use this lemma to prove the main result, which we are going to need in order to prove the theorem. So this lemma is going to be needed in the proof of the following theorem. So let A be an Abelian variety over K, L a prime different from characteristic of K. Then the representation it's rho L from gal of Ks over K to GL of VL is semi. So this is semi-simple, and the map QL tensor with the endomorphism algebra of A into the endomorphism of the Tate module as a gal Ks over K module is an isomorphism. Okay. So we are going to prove this theorem, and then once we have the theorem, then it will be fairly easy to deduce the Tate theorem. So proof Okay. So we want to prove that rho is rho L is semi-stable. Okay. So suppose that there is so there exists W, a subspace of VL of A, which is Galois stable. Right. So what we want to show that then this would have a direct summand, right? Then we can use the lemma that we just proved. So the previous lemma says that we have an element in QL tensor with the endomorphism algebra of A such that W is equal to U is a translation of VL to the left by U, right? But we know that QL tensor with this endomorphism ring is semi-simple. So these are the properties of the endomorphism ring of an Abelian variety that we saw. And what that means is that, so the right ideal, so this right ideal U, QL, right, is generated by an idempotent. Okay. So we're going to call this idempotent E. And now what we are going to do, we write this idempotent. So we can write this idempotent in two ways, right? We can write the idempotent as E times A, and where, and then we can also write E is equal to U times B, where A and B are in QL tensor with and A, right? And then, so we want to unravel what this means. So this implied, so if we take U, translated, if we translate VL to the left by U, this would be taking E times A VL. And of course, this is going to be contained in E times VLA. But if we now use the fact that we wrote E as U times B, then this would be, of course, equal to U B times VL A. And this would be contained in U VL of A, right? So that means that, so it means that W is equal to the translate of VL by idempotent, right? And so if we let, so setting This means that if we set W prime to be 1 minus E times VL of A, we see that W and W prime are complement subspaces that are above stable under the Galois action. Okay, and of course that means that rho L would be a semi-stable. So this would imply that rho L is semi-stable. Semi-simple, sorry. Okay. So now if we want to prove that the map is an isomorphism, okay. So now what we need, the key thing we need to is to recall that this map is, we want to recall that we already proved that this map is injective. Right, that we just proved that in the theorem. So we just proved that this map is injective. So that's the first thing that we want to recall. And then let's set C to be the endomorphism ring over QL of our Tate module. Okay, so what this is really, this is the commutant of VL, right? So this is the commutant. The commutant of, yeah, sorry, it's the commutant of QL and of A, right? So that's what we saw earlier. But we just proved that this, we know that QL is semi-simple. So by one of the theorem we proved earlier, so since this is semi-simple, we know that the bicommutant, this would be equal to it bicommutant, right? So we know that QL of this is going to be equal to the bicommutant, which in this case is the endomorphism over C of VL of A. And so now what it means is that, so what that means is that, so it is enough to show that for all phi that are contained in the endomorphism, not sure why I keep closing this file. It's a bit annoying. I think I know what I'm going to do next time. So close all those files. For each element in this gal of VL, we want to show that, so for every element in here and C, in C, we want to show that phi times C is equal C phi. Right. And to do that, we consider, so we want to consider the graph gamma phi, which is basically the graph of phi in VL of A, VL of A. And this is stable. So this is stable under the Galois action. And now, if we apply the lemma that we just proved, so if we apply the lemma, the last lemma we proved, then this would mean that, so if we apply this lemma, then we know that there exists an element U, which is QL of the endomorphism ring A cross A. But the endomorphism of A cross A in this case is just a matrix, the matrix algebra over QL of the endomorphism ring of A, such that gamma of phi is equal to the translate of VL of A cross A, right? And but if we take the matrix gamma, which we get by taking, if we take the diagonal matrix given by C into our endomorphism ring, right? This matrix commute with U, right? And so what that means is, so when we translate gamma phi by gamma to the left, then this would be gamma times U times VL of A square. But of course, this would be because these two elements commute, so this would be U times gamma times VL of A square. And of course, this would be contained in gamma phi. Right. But this means precisely that for all element in this VL, if we take C times phi of V, it would be phi of C times V, which implies that phi, and this is exactly what we want to prove. Okay. So now we have everything we need to prove Tate's theorem. So basically, the theorem is now a consequence of So this is the theorem. So again, so let K be a finite field. Let L be a prime. L different from P, which is equal to the characteristic of K. Then the first part says that so for every abelian variety, so for every abelian variety, so for every abelian variety A over K, rho L going from gal Ks over K to GL VLA is semi-stable. Sorry, I keep saying semi-stable. Is semi-simple. And if I have any two abelian, for any abelian variety AB, the map ZL tensor with home 0 AB to home gal KS over K of TLA, TLB is an isomorphism. Okay. So the proof really just combined So the proof I'm going to say, just combine the result above. Really, we just apply the last theorem we prove, and then that gives the proof of the theorem. So this is what I'm going to say today. For this problem set number 2 and 3, they contain several nice exercises which complement the properties of this statement, and several applications for Tate's theorem. So I encourage you to do those exercises. And as we go along, I'm also going to complement these results with some of the results we're going to see a bit later. So thank you. That's all for today.